All right, we are going to look over 3.8 today. That's the last section, actually, of quarter one and chapter 3 for that matter. Again, as promised, we are looking at solving systems of equations this chapter, and we're looking at coming up with more efficient ways. Obviously, if you think back to section 3.1 when we were looking at solving by a table and just picking values and seeing when it works in both equations, super inefficient. Graphing, super inefficient as well. Then we looked at substitution and elimination as more efficient methods, especially just solving algebraically as far as things go. Those are easier ways to get your, if you have a rational answer, those are quite easy to come up with. Last section, we looked at Kramer's rule, so using matrices to simplify the process into probably, about a minute to solve. And today we're going to look at even shortening up that process using inverse matrices. All right. So as we go into the first thing we want to look at is what is the identity matrix and what is the inverse matrix? Well, an identity matrix, you guys, is just like the number one when we talk about a multiplicative identity. That number is 1. Okay. An identity matrix, if you notice, is 1, 0, 0, 1 in the middle of the screen here. And basically what it means is when you multiply a matrix by this matrix, I, you're going to get the exact same matrix. And that's what's kind of listed down here. The nice thing about this, the order doesn't matter. So if you put the identity before or after, it's still going to give you the exact same matrix in the end. Keep in mind, identity matrices must be square. Okay. Then your entries are ones down the diagonal from top left to lower right. And the rest of the entries were 0. So if I wanted to show you an example of like a 3 by 3 identity, it would look something like this. So we have ones down the diagonal and then zeros throughout. So this is going to be an identity matrix for a 3 by 3 situation. Okay. Just remember, when you multiply by the identity, you get the exact same matrix. Okay. So in order to verify two matrices are inverses, just like, thinking about numbers, I know that 2 and 1/2 are inverses of each other because I get 1. Okay. That same idea is going to hold true with matrices. So if I multiply m times n, and I get 1, 0, 0, 1. If I multiply n times m, and I get 1, 0, 0, 1, we know they are identities. All right. Or sorry, they are inverses, not identities. All right. So we're going to multiply our matrices. We're going to go across and down, just like we did with matrix multiplication. You can see this top left entry is going to be -4 times 1/4, which is -1. And then 2 times 2, or sorry, 2 times 1/2 is 1. So that's 0. Well, immediately, right off the bat, I don't need to do any of these other entries because what number was that supposed to be? A 1. Exactly. All right. Since that's not a 1, I don't need to bother checking anything else. I know that these two matrices are not inverses. Make sure you do check both ways, mn and nm. Okay. You need to verify both do equal the identity. If both equal the identity or both products equal the identity, then you know they are in fact inverses. So let's do the same on the next one. We want to find PQ and we want to find QP. All right. So we go across and down. So we have 4/3 minus 1/3 is 3/3. We go across and down. We have -4/6 and +2/3, which is 0. We multiply across and down. We have 2/3 and -2/3, which is 0. And then we go across and down to get our final entry, and we wind up with negative 2, 6, and positive 4/3. 4/3 minus 1/3 is 1. So in fact, it did work out. What we need to do now is flip-flop the order. So we'll want to do 1/3, negative 1/6, 1/3, negative 2/3, and then we want to switch the order. All right, so we're now finding Q times P. So we do the same thing we just did. Multiply across and down. 4/3 minus 2, 6. Well, 4/3 minus 1/3 is 1. When we go across and down my second column, we have negative 1/3 and positive 2, 6. When you add those together, you do get 0. When you go across the bottom, we have 4/3 and negative 4/3. Positive 4/3 and negative 4/3 is, of course, 0. And then our last entry, we go across the bottom, down the second. We have negative 1/3 and positive 4/3. 4/3 minus 1/3 is 3/3, which is 1. You notice we got the identity with both products. So yes, the matrices are inverses. Yay! Smiles. All right. Again, like I said before, when verifying two matrices are inverses, we do need to figure out that products PQ and QP. If you get the identity with both products, you know they are in fact inverses. If you check one entry and it's wrong, it's not what it's supposed to be, you don't have to check anything else. You can just assume they are not inverses. All right. So the next piece we're going into is finding inverse of a 2x2 matrix. This pattern is something you will need to remember. Okay. It does involve determinants, so kind of keep that in mind. But this pattern, once you do it a few times, honestly, it will stick. Okay. If you notice, this number right here, AD minus BC, is the determinant of A. Okay. So another way to think about this is the inverse of matrix A is 1 over the determinant of A, and then you flip-flop entries A and D, and you take the opposite of B and the opposite of C. Okay, so it's a couple ways you can think about things, but again, the first thing you want to do with your matrix is figure out the determinants. We have negative 12 minus 7 is negative 19 in this case. So if we know my determinants, negative 19, we're going to scalar multiply 1 over the determinant by our newly arranged matrix. Remember, we switch D with A, and then we take the opposite of B and the opposite of C. And then when we multiply through, we wind up with 4 over 19, 7 over 19, 1 over 19, and negative 3 over 19. And that's the inverse of that matrix. Next situation, again, figure out the determinant first. So we have 6 minus a negative 4, which is going to be 10. So then what we do is we take 1 over that determinant, which is 10, and then we modify our matrix. So we're going to switch A and D, opposite of B, opposite of C. From this point, we'll scalar multiply the 1/10 through. So we have 3/10, negative 1/10. 4/10 is 2/5, and 2/10 is 1/5. I highly recommend you keep your answers in rational form or fractional form. It will make the process a little bit easier as we go through things. Okay. One thing to kind of touch base on before moving on is, since we are dividing by the determinant of A, like we set up here, if the determinant of A equals 0, finding the inverse is not going to be defined. Okay, so in any instance, if you're trying to use Cramer's rule, if you're trying to use inverse matrices to solve, and we figure out our determinant 0, well, unfortunately, Kramer's rule and inverse matrices aren't going to work because we can't divide by 0, okay? So if you ever encounter a situation like that, whether it be in the homework or quiz or whatever, you need to find a different way to solve the system, okay? Even if it says like use Kramer's rule, use inverse matrices, if your determinant's 0, it's not going to work, all right? So let's get into the last piece of the day, and that's using inverses to solve equations. And what I want you to draw your attention to is the system, or two-variable system in this instant. And what we're going to do is we're going to set it up as a matrix equation. So we set up our coefficient matrix, okay? If you notice, that's 1, 2, 3, negative 6. Our coefficient matrix should be pretty familiar after doing Kramer's rule. Then we have our variable matrix, okay? That finally equals our constant matrix. Some of you are probably wondering why this works out or how this works out, but if you remember, can I take a 2 by 2 and multiply it by a 2 by 1? Yes. The columns of the first match the rows of the second, and I'm going to wind up with a 2 by 1 matrix, which is in fact what a B is, okay? Furthermore, if we look at the actual multiplying process, we go across the first and down the second. So 1 times x and 2 times y should be 9, which is exactly what we have up here. Looking at the next row, we have 3x times or plus negative 6y equals negative or equals 3, which is precisely what we have down here. So hopefully you're kind of seeing the correlation between that equation or system of equations and how it correlates to our matrix equation. All right, 2 variable systems, pretty easy to solve. So I'm going to show you a 3 variable system just to kind of show you more of that challenging process as we go through things. All right, so first things first, we want to take our system and convert it to a matrix equation. So I need my coefficient matrix. So I'm going to grab the coefficients from each. So we have 1, negative 1, and 5. And then I would advise you to double check, make sure 1, negative 1, negative 4, negative 1, 3, negative 1, 1, negative 1, and 5. That is my coefficient matrix. We're then going to multiply it by our variable matrix, which in this case is x, y, z. When I multiply it by x, y, z, my first solution is 3, my second solution is negative 1, and my third solution is 3. So if you notice, again, we have this instance where we're multiplying 2 matrices together to get the third. We have a 3 by 3 and a 3 by 1. Is that operation defined? Yes. We in fact have a 3 by 1. Okay. From here, we want to figure out how to solve. Well, let me kind of go off to the side here and give you something, you know, maybe more relatable. So if I have 2x equals 4, how would you solve this? Most of you would say, well, we're going to divide by 2. Okay, which is in fact right, and we wind up with x equals 2. All right, if I told you you could not divide to solve, is there another way? And most of you are probably figuring out, well, I could just multiply by 1/2. And in fact, yes, you could multiply by 1/2 and get the same result, x equals 2. Okay, with matrices, you hopefully have discovered that we don't divide matrices. We can add, we can subtract, we can multiply, but dividing matrices does not work. So the question is, how do I get my variable matrix by itself? Well, since I can't divide by A, what I can do is multiply by the inverse. Because if you remember from the first part of the lesson, if I take an inverse and the matrix itself, I'm going to get what's called the identity matrix. The identity times anything is going to be itself. Okay? If I include the identity matrix on the left-hand side, if I do something to the left side of my equation, I also need to do it to the right side of my equation. So in order to get B, I need to find the inverse of A and multiply it by C. At this stage, you guys are probably wondering, well, that makes sense, but how do I find the inverse of a 3x3 matrix? And I will tell you the only way to do it is on your calculator at this time. You'll learn how to find inverses of 3x3s by hand in pre-calc honors, and I think actually in pre-calc general. But for this year, we're just doing 2x2s by hand. 3x3s you need to use your calculator for. So I included some screenshots below. But what you want to do is go to your matrix menu, very similarly to how you set things up for Cramer's rule. Arrow over to edit. And then you want to include your coefficient matrix. I'm just going to CE, coefficient matrix. All right. You want to do the same thing. So you want to go to your matrix menu after you get that in. And you want to arrow over to edit. But this time, instead of matrix A, like we did in the first instance, you want to do matrix B. And this is your constant matrix. Okay. And those are your answers. Okay. At this stage, once you have those two matrices set up, you want to go back to your calculation screen. All right. And you want to do matrix A, or A inverse, times B. That's exactly this calculation we're doing. We're taking the inverse of our coefficient matrix and we're multiplying it by the constant matrix. Again, how you do that is you go to your matrix menu, and instead of arrow over into edit, you just want to grab the name A inverse. You'll notice the inverse key, if you look on your calculator, is the same button you've been pressing for your matrix menu. Okay, so grab matrix A, then hit your inverse key, hit multiply, go back to the matrix menu and grab matrix B. At this stage, you can hit calculate, and surprise, surprise, your calculator is going to spit out 401, which is precisely the ordered triple solution to this problem. Okay. Again, 3x3s. You'll want to use your calculators to find that inverse. You cannot do a 3x3 inverse by hand at this stage. You will learn that next year in math. 2x2s, the expectation is you can do inverses by hand because you know how to find inverses by hand. Again, I'll show you back here. We found inverses by hand, and again, you do know how to multiply matrices together. So this operation, the inverse of your coefficient matrix times the constant, you can actually do on paper. You can obviously always check on your calculator, but that is not an expectation. But you should be able to do 2x2 inverses by hand. All right. If you have any questions, let me know. Obviously, this process looked long, okay? But once you get the setup of the system down, you should really be good to go as far as things go. So I should see the setup as a matrix equation. I should see how you're getting your answer. You then can use your calculator to come up with the answer. And those are kind of the minimums that I should see in terms of your work. All right. But that is all. If you have questions, post them to the discussion board, show up to a Google Meet, or ask me in person. Other than that, good luck on the last section of chapter 3, and I wish you the very best.